Hi everyone! In this video I'm going to be going over chapter 1.11 and chapter 1.12. So 1.11 is solving equations and inequalities graphically. So our graphical method is viewing x as a variable and then we sketch the appropriate graph. So like in our algebraic method, we use the rules of algebra to isolate the unknown x on one side of the equation. So that's shown here, where we take 3x minus 4 equals 1, then we move stuff over, and then we get x equals 5 over 3. So our graphical method is we move all terms to one side, and then we solve for y, and then we graph the equation, and then we find the y-intercept, which are the solutions of the line. So here, our y-intercept is approximately 1.7. So that would be our solution. As we can see, if you do 5 divided by 3, that's about 1.666. So that's like 1 2/3. So our x approximation is pretty close to that. So usually when you're doing graphical methods, unless it's right spot on, you usually approximate. So this is pretty good, as some equations it is difficult to solve them algebraically, or it's pretty difficult to isolate x. So that's when we do the graphical way. So here we are going to find solutions using algebraic and graphical methods. So we have x squared minus 4x plus 2. So if we're doing this algebraically, we could use the quadratic formula. So we have plug everything in. Our a is 1, our b is -4, and our c is 2. So we get 4 plus or minus square root 16 minus 8 over 2, which is 4 plus or minus square root 8 over 2. We're able to change the 8 to square root 4 and square root 2. So square root 4 is 2, so we're left with 2 square root 2 over 2. We factor out of 2, and then these 2 can cancel. So we're left with 2 plus or minus square root 2. So if we were doing this graphically, we could go ahead and make a table of our values. So we have x is -1 to 2, and then we solve and plug those in for each to get our y value, and then we could go ahead and graph it. And then so here, we graph each point, and then we're like, okay, this point is probably about 0.6, and then this point here is probably about 3.4. So we'll say our solutions are approximately 0.6 and 3.4, and then these are algebraic. So even though our algebraic solutions give us exact solutions, sometimes we are able to just approximate them by graphing them. So if you're able to, go ahead and do it algebraically, unless it asks you to do it graphically. But sometimes it's hard to get the x, and that's when we do it graphically. Okay, so solve the equation in the interval x cubed minus 6x squared plus 9x equals square root x in 1/6. So I'm going to go ahead and move the square root x to the left side, and then we have this big graph. So I'm going to go ahead and use Desmos, but you could use a graphing calculator or Desmos to do this. So I'll go ahead and pause the video and do that now. Alright, I'm going to go ahead and punch this in. So it's x cubed minus 6x squared plus 9x minus, let's see, square root. There we go. So the command for that is sqrt x. Okay, so we're going to look at where it intersects the x-axis. So at 2.177 and 3.72, and those are the solutions. Okay, so from Desmos we were able to see that x is approximately 2.18 and 3.72. So solving inequalities graphically. So algebraically, we would have 3x minus 4 is greater than or equal to 1. we would get the x by itself, and then we got x is greater than or equal to 5/3, and we would include 5/3, and then it goes x is greater than 5/3, so to infinity. So graphically, we would move all the terms over and set it equal to y. So, and then we would graph the resulting equations and find the values of x where the graph is above or on the x-axis. So we're just going to do an example to demonstrate this. So the 3x minus 4, I would just move that over. So I would move the 1 over, so I would get 3x minus 5 is greater than or equal to 0. So the y is like 0 here. But we're looking for the values. Oh, sorry. Our y is like 3x minus 5. So we're looking for the y values that are greater than or equal to 0. So here, these y values are the ones that are greater than or equal to 0. So our solutions are the x's that satisfy that. So those are like these ones. So these ones are solutions for that inequality. Okay, so here's our example. Solve the inequality 3.7 x squared plus 1.3x minus 1.9 is less than or equal to 2 minus 1.4x. So our y1 is going to be the left side, and then our y2 is going to be the right side. Alright, so we could graph it with a graphing calculator or Desmos. So I'm going to go ahead and pause the video and graph it on Desmos. Okay, so we're going to be using Desmos to do this. So I'm going to go ahead and punch in the y1 and y2 for this one. So I have 3.7 x squared plus 1.3x minus 1.9. Okay, so that's my first graph. Then my second graph is 2 minus 1.4x. Right, so we're going to look for the values of x for which y1 is less than or equal to y2. So we want our y1 is the red. There you go. And so this value, the first negative 1.454, that's the x value that corresponds to the y value where our y1 is less than or equal to y2. And then this one over here where they intersect, the 0.725 is also the x value that corresponds with the interval of the y values, these ones that are less than or equal to the blue y values, because they're underneath the blue line. So that's going to be our interval. Okay, so we're interested in the values of x for which y1 was less than or equal to y2. So this is like my Desmos graph, like on here. So to determine the appropriate interval, we're going to look for the x-coordinate of the point where the graphs intersect. So y1 is our red, and then y2 is our blue. So the values for x where the red is less than or equal to the blue, those are these y values. Okay, and then our x's that correspond with those are this one and then that one. So negative 1.45 and 0.72 is our appropriate x interval for where the y's are from y1 are less than the y's from y2, because those are the parts that are underneath the blue line. Okay, so chapter 1.12 is modeling variation. So direct variation is when one quantity is a constant multiple of the other. So if the quantities x and y are related by the equation, x equals kx for k not equal to 0, where k is a constant, we say that y varies directly as x or y is directly proportional to x, and k is called the constant of proportionality. So the graph of y equals kx describes direct variation. That's a line with slope k and y-intercept 0. So you can see it's direct variation because, for example, our p equal 0.43 d, where d is the depth and p is the water pressure. So we know p and d are direct variation because usually they're on like the same line, and we'll see for inversely variation it's like a fraction. But these p and d are both on top. So that means if pressure's doubled, tripled, etc., then the depth is doubled, tripled, etc. And that makes sense because when you go deeper in the water pressure also increases at the same rate. And the rate here is 0.43, so 0.43 is our constant of proportionality. So here's an example. The distance between you and the storm varies directly as the time interval between the lightning and the thunder. So suppose the thunder from a storm is 5,400 feet away. It takes 5 seconds to reach you. Determine the constant of proportionality and write an equation for variation. Okay, so let's go ahead and name some variables. So d is going to be our distance from you to the storm. Our k is going to be the constant of proportionality. And t is going to be the length of the time interval that it takes for between the lightning and the thunder. Okay, so our d is equal to k times t because the distance between you and the storm varies directly as the time interval. So these are directly proportional. And our k is our constant. So t, they gave us equals 5 when d equals 5,400. So we'll go ahead and plug those in to solve for k. So we get 5,400 equals k times 5. We isolate k, which is k equals 1,080. So our d is 1,080 t. So we could plug our k back in. So this is our equation for variation. All right. And then b is we want to sketch it, and what does our constant of proportionality represent? So our sketch is going to be a line through the origin with a slope of 1,080, because remember, direct proportionality is like an equation of the line with our k is like our slope. So our slope is 1,080, and it's the constant of proportionality k is the approximate speed of sound in feet per second, because of the time between the lightning and the thunder. Okay. And that's because our k, if our constant is 1,080 feet per second, that means depending on like your distance and how much time it takes to get to you, that's going to be the speed of sound for the sound to travel a certain distance to reach you. So here's our graph. They gave us 5,400, so we have that. And that's when t equals 5, so we'd have like 1, 2, 3, 4, 5. And then if we did the slope, we would get 8,860 from 5,440. So the next part is if the time interval between lightning and thunder is now 8 seconds, how far away is the storm? So our t equals 8, so we could go ahead and calculate d with our t. So d equals 1,080 times 8, which is 8,640 feet. So that's how far the storm is away. Alright. So inverse variation. So if the quantities x and y are related by the equation y equals k over x, for k not equal to 0, where k is a constant, we say that y is inversely proportional to x, or y varies inversely as x. So k is our constant of proportionality. Okay, so this one, the inverse variation, we could tell because they're on different levels. So y is like the top of the fraction, and then x here is the bottom of the fraction. So they're inversely related. So let's go ahead and check out an example and see this in action. So Boyle's law states that when a sample of gas is compressed at a constant temperature, the pressure of the gas is inversely proportional to the volume of the gas. So for A, it says, suppose pressure of a sample of air that occupies 106 meters cubed at 25 degrees Celsius is 50 kPa. We want to find the constant of proportionality and then write an equation expressing the inverse variation or inversely proportional relationship, and then sketch a graph. So let's go ahead and write some variables down. So our P is equal to pressure and V is equal to volume. So since the pressure of the gas is inversely proportional to the volume of the gas, so our P is inversely proportional to V. So we put them on different levels, and then our K is on top. So they gave us, we want to solve for our K, so they gave us that P equals 50, this is pressure, and then our V is the volume, which is 0.106 meters cubed. So we're going to do P equals 50, V equals 0.106, and then so 50 equals K over 0.106. So when we solve for K, we multiply this side by 0.106, and then so our K is 5.3. Alright, and then we're going to go ahead and graph that. So we could end up writing P equals 5.3 over V when we plug our K back in. Alright, so by graphing it, we know our V is never going to be negative because you can't have a negative volume. So we're going to go ahead and just show the positive values for V greater than 0. And then we have our 0.106, 50 point here, because the pressure is 50 here, and then this is our point. And then we go ahead and do our relationship of 5.3 for our slope. Alright, the next part is if a sample expands to a volume, I did two twos, to a volume of 0.3 meters, find the new pressure. So if V is 0.3, we could just plug that into our equation, and we know 5.3 over 0.3 is approximately 17.7. So our pressure would be 17.7 kPa. That's our pressure units. Okay, our last example is combining different variations. So we're going to be combining different, basically more variables. So Z equals K times XY. Z is proportional to the product of X and Y. So Z is jointly proportional to X and Y. So Z equals K times X over Y. Z is proportional to X because they're on the same level, right? Z and X are both on the top. And then it's inversely proportional to Y because Z and Y are, Z is on the top and Y is on the bottom. So Z varies directly as X and then inversely as Y. Okay, so let's do an example to illustrate this. So the brightness B of a light source is directly proportional to the luminosity L of the light source and inversely proportional to the square of the distance D from the light source. Okay, that's a lot, so we're going to go ahead and write the equation first from our word problem. So the B of the light source, so we're just going to write B equals, is directly proportional to the luminosity. So do that first. Write the L on top first because we know it's directly proportional. And then our K is just going to be out here either way. And then it's inversely proportional. So that means we're going to have something on the bottom to the square of the distance D. So it's inversely proportional to the square of D. I'm just going to rewrite this so it doesn't look like that. But so we have K L over D squared. Okay, there's our equation. So it asks, if distance is doubled, by what factor will brightness change? So basically, if distance is doubled, we're going to multiply distance by 2. So B equals K L over 2. And then remember, it's 2D squared, not just D squared here, because we're doubling our distance. So 2D squared. So we get 1/4 K L over D squared. And that's because we have K L over 2 squared times D squared. And then we just take out the 1/4. And then we have K L over D squared. So brightness, B, is 1/4 of the original brightness, because if we compare this equation to our original equation, this is the same, this part here, that's the same as our original equation, but we're just multiplying it by 1/4. So our brightness would be 1/4 of our original brightness, where like this here is like our original brightness. Okay, so C is, if distance is cut in half and luminosity tripled, what factor will brightness change? Okay, so B equals K, and then our luminosity is tripled, so that means 3 times L, and then our distance is cut in half. So this time we're going to do 1/2 times D, and that's going to be squared. So we have 3 over 1/2 squared is 1/4. And then we have 3 over 1/4. So I'm just pulling out the constants there. And then we're left with K L over D squared. So that equals 12 K L over D squared. So therefore, since this is the original equation again, that means brightness is 12 times the original brightness here. Alright, that's it for this lesson. And then the next video, I'm going to be talking about section 2.1. See you then.